In this lecture, we will discuss about an important topic in combinatorics, namely the principle of inclusion and exclusion. After that, we will solve a recurrence relation using the generating function technique. These are the two things that we will be discussing in this lecture. Okay. And in the case of the principle of inclusion and exclusion, we will be including certain elements and excluding certain elements, and finally we find the number of elements in a particular set. So using that principle, we calculate the number of elements in the set. So the principle is used here to determine the so now what is the main purpose of this principle of inclusion and exclusion? To determine the number of elements. Okay, so we'll be determining the number of elements in the union of two or more finite sets, sets. Okay, so suppose if I take two finite sets A and B, okay, and this would be your universal set U. Okay, so now what I can do is I can determine number of elements in A. Okay, this would be number of elements in A. Okay, and I can find the number of elements in B. Okay, the third one would be number of elements in A union B. The fourth one would be number of elements in A intersection B. Okay, and similarly the fifth one would be number of elements. Okay, elements in A only, okay, not including the intersection. Okay, and of course this diagram that I have drawn is called as the Venn diagram. Okay, so now you have got a certain way of identifying the cardinality of different sets algebraically, and the graphical representation is given by the Venn diagram here. Okay, so now if I want to find the number of elements in A union B, so now what I do is I count the number of elements in A, count the number of elements in B, and subtract the elements in A intersection B. Okay, so this part would be A intersection B. So when I count A, I will also count A intersection B, and when I count the number of elements in B, then also I will count A intersection B twice. So if I want to find the distinct elements in A union B, then I should subtract A intersection, the cardinality of A intersection B, from the sum of the cardinalities of A and B. So this, you can see this from the formula here. I have added two numbers, cardinality of A and cardinality of B are included the elements in both the sets, and I have excluded the elements in the set A intersection B, and therefore the name principle of inclusion exclusion is applicable here. So this process of using the principle of inclusion exclusion can be used in solving many combinatorial problems. Okay, so now I will give an example, simple example here, and based on this we can work out with some tougher problems here. Okay, example here. Okay, so now I will take a simple example in a class. Okay, in a class of 50 students. Okay, in a class of 50 students, 20 students Okay, 20 students play football. Okay, you know that 20 of the students play football and 16 students play hockey and 16 students play hockey. Okay, it is found that okay, it is found that 10 students play both hockey and football. Play hockey and football. Okay. Find the or determine the number of students. Determine the number of students who play neither. Okay, so now what you have to do is you have to find the number of students who do not play football as well as hockey. Okay, so how do you use it? So as I told you, we will be using the principle of inclusion and exclusion to find out the solution. Okay, so now what I do is I take this set A as the set of students playing football. Okay, playing football. So this would be the first assumption that I make, and from this I also calculate B. What is B? B is the set of students. Okay, set of students playing hockey. Okay, playing hockey. So from this you can decipher what does the set A union B represent. Set of students. Okay, set of students playing hockey or football. Playing hockey or football. This would include both also. Okay, both of the games are being played by the student also belong to this set. And you know A intersection B will be the set of students. Okay, set of students playing hockey and football. Okay, so only the set of students who play both the games are in A intersection B, and you can see that A intersection B is contained in A union B. So now what you have to do is you have to find the number of students who do not play both the games. Okay, they are not interested in playing either hockey or football. So in this case, what is the chance? So I have defined these sets, and based on these sets, you have to use the principle of inclusion and exclusion. So when I write the cardinality of A is 20. Okay, in some cases we also represent it as number of elements in the set A. And cardinality of B would be 16. That is the number of students who play hockey. So you have cardinality of B is 16. And here you are given with cardinality of A intersection B. Okay, both hockey and football are played by 10 students. So now what you have to do is you have to find the number of students who do not play both the games. So now what happens here is that I will first find out cardinality of A union B. Okay, so now first what I will do is I will use the principle of inclusion and find out cardinality of A union B. So that would be cardinality of A plus cardinality of B minus cardinality of A intersection B. Okay, so in this case cardinality of A is 20, cardinality of B is 16, and cardinality of A intersection B is 10, which is 36 minus 10 is equal to 26. Okay, so now number of students who play. Okay, so now what do you get? Who play hockey or football, okay, hockey or football is 26. Okay, so now, but what is required here in this problem? I want to find the number of students who do not play hockey and football. It is given that, now if you look at this, if you are given that the class contains 50 students. The class contains 50 students. Okay, so now what happens here? The total number of students is 50. Therefore, okay, number of students who play neither hockey nor football, okay, who play neither hockey or football is 50 minus 26 is equal to 24. So you can see that the number of students who do not play hockey or football would be 24. Okay, so now what I can do is I can also represent it is as a diagram here, Venn diagram. This would be A, this would be B, and you can see that the number of students in the intersection is 10. Okay, and now I will have 10. How do I get this 10 here? 20 minus 10. And here in this case I will have 16 minus 10, which would be 6. Okay, so now here you can see that the total number is 50. Okay, total number is 50. So outside I will have 24. Okay, so now what you can do is with this diagram, okay, I can extrapolate the formula that I obtained and I can decipher these things. Okay, these things would be trivial here. Okay, these things would be trivial. So now let me again draw this here in this slide. So I'll have like this. This would entirely contain 50. Okay, I have like this. This would be 10. This would also be 10. This would also be 6. How do I get this? 16 minus 10. And here I get 20 minus 10. And totally I have 26. So I'll have 24. So from this would be football and this would be hockey, which is A and B here. Okay. So number of students, okay, I can get this from this. Number of students playing only football, okay, playing only football is only cardinality of A, which would be 10. Okay, so in this case I can also use this formula. Cardinality of A only is equal to cardinality of A minus cardinality of A intersection B, and of course for this problem. And similarly, cardinality of B only would be cardinality of B minus cardinality of A intersection B, which would be 6, and this is equal to number of students playing hockey only. Okay, so here you can also find all these things using the principle of inclusion and exclusion, using number of students playing only hockey. Okay, so in this case these are the consequences of the principle of inclusion and exclusion. Here I am just excluding some quantity from the section. Okay, so in this case these are certain important things that you have to understand. So now what we do here is finding out the number of elements in the set, and this principle of inclusion and exclusion is useful here. Okay, so now what I will do is I will slightly increase the complexity of this example. Okay, so now what I do is I take this as example 2. Okay, what is this example? Instead of taking 2 sets, let me take 3 sets here. Okay, a survey. Okay, you have like this, a survey of 260 television viewers. Okay, 260 television viewers produced the following information. Okay, produce the following information. Following information. Okay, what are they? 64 watch sports. 64 watch sports. 58 watch films. And 94 watch news. Watch news. Okay, and 28 watch both sports and films. Okay, watch both sports and films. 26 watch both sports and news. 22 watch film and news. Okay, and 14 are interested in all the three. 14 are interested in all the three. In all the three. Okay, so how many, okay, how many people in the survey, okay, how many people in the survey, okay, are not interested, okay, they are not interested in any of these, types, Okay, how many are not interested in any of these type, and how many people are interested, okay, as I told you, are interested in news, in watching news only. Okay, so now let me just give some time so that you can just again go through the questionnaire. Okay, the questionnaire is, you have a survey taken by the television channel. Okay, and in this they have taken data from 260 viewers, and the following information were obtained by them. 64 watch sports, 58 of them watch films, and 94 watch news. So 28 of them are interested in both sports and films, 26 are interested in watching sports and news, and 22 are interested in watching film and news. So you have got certain class 14 viewers who are interested in all the three. Okay, so now what the television channel requires is that they want to know how many of the people in this are not interested in any of these types. Okay, as we did earlier, how many of them do not play any of the games in the previous example, but whereas here the complexity is slightly increased by taking 3 sets instead of 2 sets. And how many people are interested in only watching the news. Okay, so this is just a basic one. As I said, this will be a slightly an extension of what is being done in example 1. Okay, now what is A? A is the set which will be the number of viewers number of viewers interested in sports. Okay, number of viewers interested in sports. Okay, and this would be number of viewers interested in films. And third one is the number of viewers interested in watching news. Okay, so now this is the given one. So now what I have to do is, from this I have to calculate the cardinalities, and from that I require the answers for two of them who are not interested in any of the types, and the next one would be how many people are interested only in, how many persons are interested only in watching the news. Okay, so now let me move to the next slide. Okay, so that we can calculate this. Now I take cardinality of A. Okay, now I will take cardinality of B, cardinality of C. Okay, cardinality of A intersection B, cardinality of A intersection C, and cardinality of B intersection C, and then I have cardinality of A intersection B intersection C. Okay, so this was given to be 14. Okay, that is all the three, interested in all the three is 14. 22 watch films and news, 22 watch films and news, and 28 sports and news item, 28. Okay, sports and news, sorry, not 28, 26. This one is 26. Okay, so A would represent the sports, B would represent the films, and C would represent the news items. And now what is C? C is 94, B is 58, and C is 64. Okay, so now what is required here? Let me write here. A is sports. Okay, B would be films, and C would be news. Okay, so now what is required is you have to find the number of viewers who are not interested in any of these three. Okay, so now what I will do is, first I will calculate A union B union C, cardinality of each. So I have to extend the formula here. This I can do it using B union C as some D, and then I can use the previous result and I can expand this. So I will have like this: cardinality of A plus cardinality of B plus cardinality of C minus cardinality of A intersection B minus cardinality of A intersection C minus cardinality of B intersection C plus cardinality of A intersection B intersection C. You can just use the principle of induction and then do it. Take B union C as D, then find A union D using the previous expansion that I used in example 1, and then you expand B union C, replace D with B union C and expand it, you will have this. Okay, so now what I will do is, I will just substitute these values here. So I will have 64 plus 58 plus 94 minus 28 minus 26 minus 22 plus 14. Okay, so now when I do this, when I strike this out, I will have minus 8 here. So this would give you 72 122 plus 94 minus 40 34 54 minus 8 minus 62. So when I calculate this, 60 plus 94, this would be 154. So in this case, what happens here is that number of viewers interested in sports or film or news is 154. Okay. So what I do is I want number of viewers not interested in any, not interested in any is, okay. So I have to subtract this 120, 154 with the total amount. Total amount is 260. Okay, is 260 minus 154. This will be 46 106. Okay, so the answer here, who are not interested, okay, who are not interested in any of the, okay, who are not interested in any of these is 260 minus 154, which would be 106. Okay, and now what I have to do is I have to find out the number of viewers who are interested only in the news. Okay, so now let me again take this Venn diagram so that you can easily understand this. Okay, so now I'll have 3 sets instead of 2. Okay, so now let me draw like this. This would be A, this would be B, and this would be C. Okay, as usual, A represents let me write here, A represents sports. Okay, number of viewers who like sports. B would be film, number of viewers who are interested in film, and C would be the number of viewers who are interested in news. Okay, now let me write down this like this. 14 are interested in all the 3. 22 watch films and news. Film and news is 22. So I'll have 22 minus 14, which would be 8 here. Okay, who are interested only in film as well as news. Okay, and then now I got 26 interest, watch both sports and news. Okay, 26 26 minus 14, that would give you 26 minus 14. Good. 26 minus 14, that would give you 12. Okay, so I have like this. Now what is the number of person who watch sports and films is 28. 28 minus 14, that would be 14. So now let me write down here like this. Cardinality of B intersection C only, okay, is cardinality of B intersection C minus cardinality of A intersection B intersection C. Okay, you can just write down this formula from this, and this turns out to be what is B intersection C is 22 minus 14, this would be 8. Okay, so who are interested, so in this case what happens here is that B is number of viewers who like film and news is 8. Okay, so now I have incorporated this part. Similarly, A and C, cardinality of A intersection C only is cardinality of A intersection C minus cardinality of A intersection B intersection C, and this would give you 26 minus 14, this would give you 12. Okay, so here you get number of persons interested in what shall I say, films and news. Sorry, not film. A represents sports, is that right? So interested in sports and film, news is 12. Okay, so now what I want is, I want the number of persons who watch only news. Okay, so now what I want is, I'll have like this, let me write here, number of C only is equal to cardinality of C minus cardinality of A intersection B only minus cardinality of A intersection B intersection C minus cardinality of B intersection C only. Okay, so now here it is given that the cardinality of C turns out to be 94 minus, I have calculated A intersection okay, so now what is that? B intersection A intersection C, not B here, sorry, A intersection C. What is A intersection C? A intersection C is 12 only, is 12 minus 14 minus B intersection C is 8. Okay, so now here I have 26, 34, so I get the answer as 60. Okay, 60. And now you can see here, this would be 98 minus 12 minus 14 minus 8. And similarly, here you have 64 watch sports. So I have 64 minus 14 minus 14 minus 12. And here I have 58 watch films. So I have 58 minus 14 minus 14 minus 8. So I can find the number of viewers who watch only film, who watch only news, who watch only the sports, and I can find a combination using this. And of course here I have used the Venn diagram, as well as I have also given you the algebraic formulation of finding out the number of elements in the set using the principle of inclusion and exclusion. Okay, so here we come to an end to example 2. Okay, so now in the first example I have given with 2 sets. In the second example I have given with 3 sets. Now let me extend this. Okay, so if A1, A2, so on, AK are finite sets, okay, are finite sets, then cardinality of A1 union A2 union A3 so on union AK, this would be cardinality of A1 plus cardinality of A2 plus so on plus cardinality of AK. Okay, now let me write down like this, minus summation of I less than j cardinality of AI intersection AJ plus summation I less than j less than R cardinality of AI intersection AJ intersection AR minus so on plus minus 1 whole power k cardinality of A1 intersection A2 intersection A3 intersection so on intersection AK. Okay, so here alternatively you have plus and minus, and you have the pair of sets, then pair of sets taken 3 at a time, then 4 at a time, 5 at a time, and at last all the k. So in this case, this is the generalized version of this formula. Okay, this generalized version of this formula I have used for 2 sets and 3 sets. I have generalized it to k sets. This you can prove, as I told you, take A2 union A3 so on union AK as B, then expand A1 union B, and then replace B. Again you have to continue this process k minus 1 times in order to get the required result here. Okay, so this is the generalized form of the principle of inclusion and exclusion. So using this Okay, let me solve a problem in number theory. Okay, um, this would be again principle where we have used here. Let me take this as a problem here. Okay, using principle of inclusion and exclusion. Principle of inclusion and exclusion. Find the number of primes. Find the number of primes between 1 and 100. Okay. So now I want to count the number of prime numbers between 1 and 100. Okay. So how to do it? Okay. So now let me take like this: A be the set of numbers divisible by 2, and B be the set of numbers divisible by 3. C be the set of numbers, okay, divisible by, we'll have like this, divisible by 5. Okay. Okay, C be the set of numbers divisible by 5, and D be the set of numbers divisible by 7. Okay, so now the basic part would be, I will just take the square root of 100, which is 10. Okay, so now what I do is, I find the numbers which are divisible by 2, 3, 5 and 7, and of course you can see that these are all numbers less than 10, which is nothing but square root of 100. So now what I do is, I remove this multiples of 2, 3, 5 and 7, so that I will get the numbers which are not divisible by these 4 numbers, and therefore there is a chance that those numbers would be the prime numbers. So this is the process that I am going to use here. So now I have 4 sets. So now what I will do is, I will calculate the number of elements in each set, and then use the principle of inclusion and exclusion to find the required result. Okay, so now what do you get? Cardinality of A would be 50. Okay, this is nothing but 100 by 2. Okay, and similarly cardinality of B would be 33. 33 into 3 would be 9. Cardinality of C would be 20. 100 by 5, which is 20. Cardinality of D would be divisible by 7. Okay, so let me write like this: 7 ones are 7, so I'll have remainder 30, 17. Sorry, not 17, 14. 14 into 7 is 98. 14 into 7 would be 98. So I have this. Then I get cardinality of A intersection B. That is a set of numbers divisible by 2 or 3. 2 into 3 is 6. So I will have 16. 16 into 6 is 96. So now I take cardinality of A intersection C. Okay, what is the intersection C? Numbers divisible by 2 as well as 5. So I will have 10. Okay, 10 numbers which are divisible by 2 as well as 5. And then third one would be cardinality of A intersection D. Okay, 14. Okay, 14. 14 into 7. Okay, 98. So I'll have A intersection D as 7. And then the next one would be cardinality of B intersection C. 15. 15 into 6 is 90. Okay, then I have to calculate cardinality of B intersection D. Okay, B intersection D is 21. 21 into 4 is 84. Okay, so now I have exhausted B. Now I should have cardinality of C intersection D. C intersection D would be 35. So I'll have 100 by 35, which will give you quotient 2. So I have two numbers which are divisible by 5 as well as divisible by 7, which will be 35 and 70 here. Okay. So now I have taken all the combinations of 2 at a time from 4. Okay, now let me take 3 at a time. A intersection B intersection C. I have to find the cardinality of numbers divisible by 2, 3 as well as 5. So I have 2 into 3, 6. 6 into 5 is 30. 100 by 30 give you 3. And then I would calculate A intersection B intersection D. Okay. What is A intersection B intersection D? 2 into 5, 10 into 7, 70. I will have 1. Okay. That is a divisible set of numbers which are divisible by 2, 3, 2, 5 and 7. Okay. 2, 5 and 7. That would be 70. So I will have only one number. So I have this. And then the next one would be cardinality of A, C and D. Okay, what is cardinality of A, C and D? A, B, D. Okay, so I think I have made some error here. What will be A, B and D? A, B, D. 42. Okay, 76, 42. So I'll have into 2, 84. So this would be 2 and this would be 1. Okay. So now I have to take 3 at a time. So I have taken A intersection B intersection C. Then I have taken A intersection B intersection D. And then I have taken A intersection C intersection D. Now what is left out? B intersection C intersection D, which would be 15 into 7. 15 into 7 is 105. So 105, you don't have any numbers divisible by 3, 5 as well as 7. So this would be 0. And then of course cardinality of A intersection B intersection C intersection D would also be 0. That is the numbers which are divisible by 2, 3, 5 and 7. So in this case, this gives you the number of elements. So from that, what I do is I find the number which are divisible by, find the numbers which are divisible by 2, 3, 5 and 7. Okay, 2, 3, 5 and 7. Let me do it here in the next slide. Okay, so now what do I get? When I do it, I will have like this. Okay, so now what happens here is this. Okay, I will have like this. Let me write down this. N of A union B union C union D. This is equal to N of A plus N of B, number of elements in B, plus N of C plus N of D minus, let me write down like this, summation of N of A intersection B. Okay, so I take all the combinations here, plus N of, plus summation N of A intersection B intersection C minus N of A intersection B intersection C intersection D. Okay, so now I have to simplify this. I will have 50 plus 33 plus 20 plus 14 minus 16 minus 10 minus 10 minus 7 minus 6 minus 4 minus 2 and then plus 3 plus 2 plus 1 plus 0 minus 0. Okay, so now when I simplify this, I will have number to be 78. So here number of elements not in set A or B or C or D is 100 minus 78, which is equal to 22. Okay, so now if you look at this, you can find that out of the 100 numbers, you have 22 numbers which are not divisible by 2, 3, 5 or 7. Okay, so now what I do is I take like this. Okay, so the first part would be like this. Let me eliminate 1. Okay, I have like this. 1 is not divisible by 3, 5, 2, 3, 5 or 7, and is also not a prime. Therefore, okay, you have 21 numbers not divisible by 2, 3, 5 and 7. Okay, and here 2, 3, 5, 7 are prime numbers. Therefore, number of primes between 1 and 100 is 21 plus 4, which would be 25. Okay, you can just use a simple calculation, namely the principle of sieve of parenthesis, to identify that you can find 25 prime numbers between 1 and 100. Okay, so you have 2, 3, 5, 7, then next one would be 11, 13. Okay, so you can list out the number of primes between 1 to 100, and here I have used the principle of inclusion and exclusion to find the number of primes between 1 to 100. Okay, so now what I will do is I will stop with the principle of induction, principle of inclusion and exclusion here, and now I will move to the next topic, what is called as the principle of generating functions. Okay, so now using the principle of generating functions, you can find out, okay, you can find out a solution to the recurrence relation. Okay, so that would be the next topic. Okay, let me write down here, generating functions. Okay, this generating function is that this is used to solve recurrence relation. Okay, this is used to solve recurrence relation. Okay, let me explain what is this recurrence relation is. Okay, an equation that expresses, okay, an in terms of, okay, in terms of one or more of the previous terms, one or more of the previous terms, okay, previous terms of the sequence, okay, namely a0, a1, a2, so on, an minus 1. Okay, for all integers, n greater than or equal to n0, where n0 is non-negative integer, is called, okay, this one is called as a recurrence relation, okay. So here you have this, is called recurrence relation. Okay, it's called a recurrence relation. Okay, now let me write down an example like this. an is equal to an minus 1 plus 3an minus 2, where n is greater than or equal to 2. A naught would be 1 and a1 would be 2. Okay, so now what I do here is I substitute n is equal to 3. I have a3 is equal to a2 plus 3 a naught. A2, oh sorry, I have to substitute first n is equal to 2. When I substitute n is equal to 2, I will have a2 is equal to a1 plus 3 a naught. a1 is 2 and a naught is 1, 3 into 1, which would be 5. So here I have a3 is equal to a2 plus 3 a naught. a2 is 5, and when I substitute n is equal to 3, I will have this to be 1. Okay, a2 plus 3 a1, n is equal to 3. So 3 a1, a2 is 5 and a1 is 2. 3 into 2, this would give you 11. Okay, I have 11. And similarly, when I substitute n is equal to 4, I will have a4 is equal to a3 plus 3 into a into 2. Okay, a3 is 11 plus 3 into 5. So this would be 15 plus 11, 26. 15 plus 11, 26. So here the sequence would be like this: 1, 2, 5, 11, 26, so on. So this would be the sequence, and this sequence is represented by this recurrence relation. It is represented by this recurrence relation, and using this you can find the solution to any general recurrence relation using the generating function. So that is the idea behind this. So now what we are trying to do is, given a recurrence relation, we will be translating it into an equation which is a polynomial in Z, and that polynomial will be called as the generating function, and use certain operations on the generating functions and find out the solution to the given recurrence relation. So that is the thing that we are going to do now. Okay, so now what we do is we write like this: we can translate okay, the recurrence relation. We can translate the recurrence relation into an equation, okay, involving generating function. So now what we will do is, we will identify a method how to identify a recurrence relation with the generating function. Okay, so now given a sequence, let me write like this. You have a sequence like this. Okay, given a sequence, I have a sequence. Given a sequence an, okay, n greater than or equal to 0. How do I form the generating sequence? The generating sequence is g of z, which would be a0 plus a1 z plus a2 z squared plus so on, plus an z power n plus so on. Okay, so now you have a generating sequence like this. Okay, now I associate this with the sequence. So let me give you an example here. Okay, a simpler example here. Okay, now what I do is I take the sequence, 2, 2, 2, 2, so on. Okay, I just take a sequence in which every term is 2. Okay, so in this case g of z would be 2 plus 2 z plus 2z squared plus so on. When I remove this 2, I'll have 1 plus z squared plus so on, and you can see that its sum is 1 by 1 minus z if modulus of z is less than 1, and this turns out to be the closed form of the generating function. Okay, so now this is the process that you can do here. Okay, so now let me take this example, second example. Okay, example 2, and the sequence here is this. Given sequence is 1, 2, 3, 4, so on. Okay, so now what I do is I construct the generating function g of z, 1 plus 2z plus 3z squared plus 4z cube plus so on. So this would be 1 by 1 minus z whole squared if modulus of z is less than 1. Okay, and again this would be the closed form. Okay, see, you can use any type of function, e power z. Okay, 1 plus z squared by factorial 2 plus z cube by factorial 3 plus so on. Okay, you also have another function, e power minus z, 1 minus z plus z squared by factorial 2 minus z cube by factorial 3 plus so on. Okay, so you have another type of function, what you call it as log 1 plus x. So you can use any of the function and its sum, namely the closed form, in finding out the solution of a recurrence relation. Okay, so now what I will do is I will just take an example here, and I will give you a method of finding out a solution to the recurrence relation using the generating function. Okay, so now solve an is equal to 3 into a into n minus 1 plus 2 with n greater than or equal to 1 and a naught is equal to 1 using generating function technique. Okay, using generating function technique. Okay, so this would be the basic one. Okay, so now what I do here is I multiply an left hand side and right hand side of the given equation with z power n. Okay, so now I'll have plus 2 into z power n. Okay, 2 into z power n. And now if you look at this, n is greater than or equal to 1. So now what I will do is I will sum it between n greater than or equal to 1 an z power n and 3 times summation an minus 1 z power n, where n is greater than or equal to 1, plus 2 times summation z power n, where n is greater than or equal to 1. Okay, so now what I will do is I will take g of z as summation a naught z power n. The index is between n to infinity. Okay, so now when I expand this, if you look at this, when I expand this, I will have a1 z plus a2 z squared plus so on. And this would be 3 times a naught z plus a1 z squared plus a2 z cube plus so on. And of course this would be 2 times z plus z squared plus z cube plus so on. Okay, so when I rewrite it in terms of z, I will have g of z minus a naught. And here when I remove z as a common factor, this would be g of z, a naught plus a1 z plus a2 z squared plus so on, which would be 3z into g of z. And now when I take z as a common factor here, if you look at this, when I take z here, I'll have 1 plus z squared plus so on, which would be 2z divided by 1 minus z. Okay, so now if you look at this, this will be 2z by 1 minus z. Okay, and now I know the value of a naught. A naught is given to be 1. Okay, so now what I will do is I bring this term 3z into z minus 3z into g of z to the left hand side. I'll have g of z minus 3z g of z. This would be 2z by 1 minus z plus 1. Okay, so when I simplify this, I'll have 2z plus 1 minus z by 1 minus z. This turns out to be 1 plus z by 1 minus z. So when I simplify the right hand side, I'll have 1 minus 3z into g of z. This would be 1 plus z by 1 minus z. So g of z would be 1 plus z by 1 minus 3z into 1 minus z. So this would be the closed form. Okay, this would be the closed form of the given relation, given recurrence relation. Okay, so now this would be the closed form of the given recurrence relation. Okay, you can have like this. The given recurrence relation. Okay, this will be the closed form. Okay, I use the partial fractions to split this. So I have a by 1 minus 3z plus b by 1 minus z. Okay, this would be g of z. Okay, so now I have, let me write it down in the next slide. 1 plus z by 1 minus 3z into 1 minus z. This would be a by 1 minus 3z plus b by 1 minus z. So 1 plus z would be a into 1 minus z plus b into 1 minus 3z. When I substitute z is equal to 1, I'll have 2 is equal to b into 1 minus 3, which implies b is equal to minus 1. And when I substitute z is equal to 1 by 3, I will have 4 by 3 is equal to a into 2 by 3. Okay, 3 gets cancelled here, and from that I can get a is equal to 2. Okay, so in this case, your g of z would be 2 by 1 minus 3z, and b would be minus 1 by 1 minus z. Okay, so now what I do is I write this 1 by 1 minus 3z as 1 minus 3z whole power minus 1 minus of 1 minus z whole power minus 1. So I want to find the coefficient of z power n. Okay, so now from this I will have this to be 2 into 1 plus 3z plus 3z whole square plus so on plus 3z whole power n plus so on minus this will be 1 plus z square plus so on plus z power n plus so on. So your nth term coefficient of z power n would be 2 into 3 power n minus 1 power n, which is 2 into 3 power n minus 1. So this would be the solution. This would be the solution to the given recurrence relation. So I have just used the series and I have calculated the solution to the given recurrence relation. Okay, so here this completes this particular problem. Now let us recall what we had done in this lecture. We first studied about the principle of inclusion and exclusion. And using this we were able to find the cardinalities of set. Okay, cardinalities of a given set. Cardinalities of a given set. And then the second part was generating function technique. Generating function is used to solve a recurrence relation. Recurrence relation. Okay, these two were discussed in this particular lecture. And if you have any queries or doubts, you can mail to Venkatakrishnu at max.sastra.edu. I'll be happy to answer your